Hello everyone. Uh, Today's session is on graphical solution of linear programming. So this is the third session, and today we are going to solve maximization problem graphical. So let's start with the problem. Here we have the problem. A paint company named Palette wants to produces wall paint. And so it produces two types of paint, interior paint and exterior paint. And it uses two raw materials, mix A and mix B. And the quantities required for the interior paint and exterior paint are given in the table. So as you can see that exterior paint requires 6 units of mix A and 1 unit of mix B, whereas interior paint requires 4 units of mix A and 2 units of mix B. So, and also the maximum quantity available of each of the two ingredients are also mentioned in this table. And also we can see that the profit per unit of the interior paint and exterior paint in terms of $1,000 is also mentioned in this table. So let us first frame this problem. So let's say that the amount of interior paint is say X1 and the amount of exterior paint is say X2. So this is X1 and X2. So these are the two quantities. And so my problem here will be, so if I take this two variables, so I can write the problem as maximize. So this is maximizing profit. So let me write it as y is equal to 5x1 plus 4x2. And the constraints are 6x1. So this is mix A constraint plus 4x2 because mix A has the maximum availability is 24. So the total amount should be less than equal to 24 because that is the maximum amount available. Similarly, for mix B, it will be x1 plus 2x2 because that is the total quantity of mix B required producing the two paints, x1 quantity of paint 1 and x2 quantity of paint 2, and so this will be less than equal to 6. And also I've got this profit. So this 5 is per unit profit from exterior paint and this is from interior. Apart from this, there is another constraint. So let's see. Now this says that maximum daily demand for interior paint is 2 tons. So here we get another constraint, that is x2, that is the interior paint, will be less than equal to. And of course, finally, we have the non-negativity constant, that is x1 and x2 are greater than equal to 0. Okay, so let's see how the problem finally looks like. So this is the problem, this is the objective function, and we have the constraints. Now, like we did in the previous video, that is the minimization problem, here also we'll convert these into equations. So we'll go for the first constraint, that is the mix A constraint. Now this is the mix A constraint. We convert it into the equation form to get the boundary. And what we did first is we set x1 to 0. X1 is equal to 0. If we put x1 equal to 0, then this term vanishes. And so we have 4x2 is equal to 24. And so x2 is equal to 6. So we have the first point 0, 6. Then we set x2 equal to 0. Right? So we set x2 equal to 0. And so this part vanishes. And so we have 6x1 is equal to 24 and x1 is equal to 4. Yes, 4, 0, done. So let's now plot it on a graph and see how it looks like. So we have plotted this on a graph. So this is 0, 6, this is 0, 6, and this is 4, 0. Now, let us now go to the other constant, that is mixed B constant. And we set it again equal to as a in terms of an equation. And then again we set x1 equal to 0. And so we'll have then x1 is 0. So we have 2x2 is equal to 6. And so x2 is equal to 3. So we have this first point. And then we set x2 equal to 0. Right? So we set x2 equal to 0. And so x1 is equal to 6. And we get the second point, that is 6. So we plot this point on the graph. So we get 3, 0, oh, sorry, 0, 3 and 6, these two points. Right? And now we have one final constant, that is x2, that is the maximum demand, that is x2 is equal to 2. So we plot this directly on the graph, and so this is x2 is equal to 2. This is x2 equal to, because we are measuring x2 on the vertical axis and x1 on the horizontal axis. So since these are less than equal to constant, this is the feasible set. As you can see, this region is the feasible set, and we can mark this. Say, let's say this is one extreme point A, this is B, this is C, D, and E. So this A, B, C, D, and E, this region is the feasible region. So my optimal solution has to be a part of this visible region. And as we have seen in the minimization problem, here also it will actually be one of these extreme points that I mark A, B, C, D, E. Let's see which one. So first now we have to go to the objective function. So let's go to the objective function. So this is the objective function. So say z is equal to 5x1 plus 4x2, and we set an arbitrary value of z. So we write, let's say the profit is equal to 10. We start from this point, and then we are going to change it to optimize it. And we have to first optimize it in terms of, we have to maximize in terms of the feasibility constants. Now, so here again we put the same, we do the same exercise. X1 is equal to 0. So 4x2 is equal to 10. So x2 is equal to 10 by 4, that is 2.5. And we get the first point, that is 0, 2.5. And then we set x2 is equal to 0, and we get 5x1 is equal to 10. So x1 is equal to, so we get 2, 0 as the other point. Right? And now let us plot it in the previous diagram. So this is the diagram, this is the objective functions. This one is the objective function, this line, right? So this line is the objective function, this green line. And what we have to do, this part is in the feasible region, but it is not optimal because I need to maximize. So I have to move it towards the right. upwards. So that profit increases. So here profit is 10. I have to increase it as much as I can, maintaining the visibility. So let's move it right. So we have moved it right. So still now we can, there is further scope of moving it. So we move it. And here, further rightwards, it will be outside the visible region. So this is the optimal point. This is the solution. Right? So this is the amount of um, x1 and amount of x2 that I get gives me the solution. Okay. So, so we can see that what we have got is here, if I drop it down, I can see that x1 is equal to 3 and x2 is equal to, it is between 1 and 2. So the midpoint, so it is 1.5. So let's see. So we have x1 is equal to 3, x2 is equal to 1.5. And we put these two values in our objective function. So 5 is 15 plus 6, that is 21. So this is the maximum profit. Let's see whether it's visible or not. It will be visible because it's in the visible region. So if I put it here, so 6 into 3 is 18, and so I have 6. So 6 threes are 18, and 4 into 1.5, that is 6. So it is exactly satisfied. 24. Then this is 3 plus 3 is equal to 6, so it is exactly satisfied. And then I have x2 less than equal to 2, so x2 is 1.5, so it is less than. So all these are satisfied. Of course, all are positive, not negative, so that is also satisfied. So we have solved the maximization problem graphically. So we'll come back again in the next session with the simplex problem. Though it is named simplex, many students find it very complex, but we'll try to do it in a make it as simple as possible. So we are coming with the next session solving by the simplex. So till then, goodbye everyone. Hope you like the classes. Thank you.